Hi, so my name is Anendo, and today I'm going to talk about engineering ethics and roboethics for surgical robots and medical device. I'm going to try to go really fast on this. There's a lot of info, and I already did a video that has a lot of info, but I'm going to try to make this shorter just so it's within the time allotted. So let's get started. Come on. All right. So what is roboethics? So the concept of roboethics, it just mostly applies to the type of approaches that engineers, designers, manufacturers, even humans in general use to address some of the ethical concerns that are arising from uh, engineering or some of the cultural, societal, and technical issues that arise uh, in the course of trying to promote or trying to reach some objective. And then in the class, there's three type of robo ethics we discussed: minimizing potential divide, and then robots having a inbuilt presumable morality. And then at the third point, it's mostly for robots to be able to self-consciously conduct certain actions. And then we also discussed will-based theory and interest-based theory. Will-based mostly applies to human, while interest-based mostly applies to robots. Next slide. All right, so in this specific article, they discussed 6 different facets to medical ethical decisions. And there's autonomy, benefits, non-maleficence, justice, truthfulness, and dignity. So autonomy is like the decision for the patient to decide what they want to do in a procedure. Benefits is mostly related to acting in the best interest of the patient. Non-maleficence is not to harm the patient. Justice is just making sure equality for all patients to the best of their abilities. Truthfulness is not being deceptive and being transparent in the process. And dignity is just kind of a sign of respect for the whole industry as a whole. One specific aspect they mentioned in the reviews telecare and how there's different type of challenge that occurs from like different type of data being lost, some of the compromises for the patient, data, stuff of that nature. Next slide. So this specific slide is just some of the engineering ethics. These are, to be clear, these are not legal binding in terms of like state boards are the only entity that could create some liability to like people that violate it. But these are just ethics and they're not enforceable. But these are just guidelines people use for ethics or engineers for best practices. And some of them kind of tie towards like the medical aspect, such as the trust for faithful agents or trustees, also performing areas of competence, acting in a truthful manner. There's similar parallels to that of the medical ethics. And next slide. So, first part of the presentation is going to have some lit reviews that discuss current engineering ethics with design and development of surgical robots and biomedical devices. So, one of them's for like osteo, like for bones, a specific type of surgical robot that can handle that operation. And then one's for a pill within endoscopic procedures. And those are actual events that are going to be, or like actual experiments that will be discussed. And then, uh, and then one important aspect is it's important to differentiate between robo ethics and robot ethics. So robo ethics is basically how robots should act. So it's kind of ties the Asimov law with what they should do in the first law, second law, and third law. Robo ethics, on the other hand, is how like engineers, designers, manufacturers should implement like how they should take into account ethical issues in the course of designing certain type of products, and also incorporating the 3 terms that I've mentioned and those type of methodologies when trying to design the robot. And then the presentation will give a theoretical formulation for like a Da Vinci robot and a hypothetical to get it to level 2, given it's in level 0 and level 1 right now. And then it'll tie it to Aristotle, deontology, and utilitarianism. So next slide. Come on. Okay, this is just technical background. I'll go fast on this. There's like, it's similar to a car. There's level 0 and level 5. Level 0 is almost no involvement with the surgical robot. Like, they can't do anything autonomously. Level 5 is they can handle the whole procedure by themselves. There's certain procedures such as colectomy, appendectomy, gallbladder removal. These are just some procedures that it's capable of doing. And then Da Vinci robot's going to be the most commonly one discussed because it's also FDA approved. And but also it's very expensive at $1.5 million. To the right is a picture of the Da Vinci robot. One's like for an open heart situation. This one's where you put in like the doctor has certain levers and buttons. They press them, and then it allows the utensils to be operated within a surgical operation, and then there's controlled, automatic, and semi-automatic. So Da Vinci is actually controlled. It's considered controlled because the surgeon has to manually input certain type of functions into it. But they're trying to there's a lot of research going on to make this into like a semi-automatic. So that's what my formulation is going to talk about to try to get this to semi-automatic and ways to make that happen. So, and I think I mentioned advantages is like the teleoperations that I talked about, where a surgeon could operate from a different country. Another is some of accommodating for some human errors or like capabilities. Humans like lack of dexterity. Sometimes robots are more, they have more dexterity. Also, there is, as I mentioned, also robots are able to conduct certain operations more accurately. They could also do an operation beforehand through simulation before the actual surgery occurs. Disadvantages, though, is there's a lot, to put it lightly. There's legal aspects. There is culpability in the situation that a robot has to decide how to go about and like in a court of law whether they're going to be held accountable and a certain type of death. There's also breakdown software connectivity issues. It's expensive again, and it's a relatively new field, and challenges are constantly arising. And these are just the summary of the three ethical terms. Virtual ethics mostly deals with the character performing an action. Uh, yeah, so there's also prudence, practical wisdom, eudaimonia, which is a sense of happiness, and Aristotle's definition of that is kind of different from how we humans interpret happiness. And then there's deontology, which studies duty, obligations, morality, without considering consequences or the character. And yeah, again, it doesn't take really emotions. It's just a lot of strict duties or like moral things that are encompassing of all rational human beings. Utilitarianism focuses on the right and wrong based on the outcome of an action, based on the premise it's generally good if it has a great net effect on the greatest number of people. There's quantity and quantitative aspects to it. This quantitative is more based on Bentham, and then quantitative was what Mill proposed, given Bentham's emphasis on quantity. But again, long story short, we really look at the outcome to determine it from a utilitarianism standpoint. Then Asimov's three law, I think I made that difference. It's kind of robot ethics. What should they do in the first, second, and third? First idea, don't harm a human being for the first law. Second law is if a human instructs a robot to make an immoral command, don't do it. And then the third law is its concept of self-preservation as long as the first and second law aren't violated. And all right, so I'm gonna get started with the lit review. First one is just it kind of talks about general concepts and how to design a robot to not conduct harm in different type of industry, but they did talk about surgical robots. First concept is non-maleficence, so just the idea of not harming a patient. Some challenges are about self-autonomous agents, given that robots are self-autonomous agents and they don't have the same moral status as like humans. The way to train them is also going to be different. So the example they gave was how they train dogs, and how you train a child is different than how a robot would be trained. And that also impacts how the AI and machine learning algorithms implemented. Another action incorporates scenarios to prevent harms in the first place from occurring. So if it fails to not act, it's equally guilty as if it did the actual harm. So situation is if the robot failed to remove a surgical sponge, it's equally guilty than if it actually removed the sponge and actually damaged like a tissue or an organ. And then the second aspect is being able to preemptively identify and assess potential harm from a robot being emotionally connected to a patient. So example they gave is for like emotional, like for, at least for elderly patients, sometimes they're prone to be emotionally connected to like a therapy doll or not. Yeah, therapy dog I meant to say, but in that situation, what ended up happening is the robot would have to make uh, processes in place to make sure they don't do certain type of actions that could induce them to be emotionally connected, because that's going to inflict harm on the patient. So that's one part of this, the technical aspect. And then The second aspect is FDA doesn't have a formal way for physician training or training for medical devices. So within the US, it's kind of the use of surgical robots is kind of there's no strong structure, so there's more leeway in terms of being able to utilize this and lack of regulations and stuff. But the scenario they talked about is if it was implemented in another country and a different jurisdiction, some of the experiments that one might want to do in another country might not be applicable because it might not even be possible based on the government laws. So that's where a challenge is. And then the second aspect is jobs potentially being replaced. And the specific example they gave is anesthesiologist, potentially with the invention of an automated sedation system by Johnson & Johnson. And then I underlined three suggestions that different people had in the article and how Da Vinci robot should be learning algorithmic behavior. One is kind of the black box approach, where it takes and records their specific movements within the procedure, records that information, and then that's how, based on those performance metrics and the movement matrix, they could determine failure analysis, and that's how they could also improve their software long term. The second idea is based on Da Vinci robot learning from the hand movement patterns of a surgeon. So the surgeon's going to do this, is going to be connected to a device that records the hand movement of the surgeon, and then based on that info, Da Vinci robot's going to learn it. And so essentially kind of ties to the concept of taking a human's command, or like placing emphasis on a human over what the robot thinks or the will of a robot. And then another aspect is, from an engineering standpoint, engineers kind of look at it from how a self-autonomous vehicle is being engineered, where there are risks, obviously, but the cost of doing business in terms of being able to deliver a surgical robot, some of those inherent risks are going to be low cost in comparison to the actual benefits, and the mere fact that surgical robots are capable of handling things that humans can't. So that's kind of the idea, and it kind of ties to utilitarianism with the risks not being too substantial compared to the benefits, like the risk being kind of minimal and compared to the benefits that arise from surgical robots. And then they envision that it's going to be similar to like a self-driving vehicle, where there's always going to be the surgeon's always going to have to work alongside the surgical robot to safeguard the patients and keeping the doctors in the loop. Next slide. Literature 3 is this is like an endoscopic pill, or a pill that can be used in endoscopic procedures. So it could also deliver drugs autonomously. But one thing that was analyzed is the level of autonomy of the robot and then the level of risk that it poses on the patient. So this was controlled in terms of these, before the test starts, they used a metric to evaluate ethical risks to the patient, and then also they determine how much autonomy the robot's going to have throughout the course of that project. And then based on that, they just set a certain type of baseline for the autonomy, and then they try to see if it met that objective or didn't meet the objective for those situations. So in essence, the co-design of this process changed, and they also involved a lot of stakeholders. They involved government agencies, designers, engineers, a lot of industrial engineers, you name it, every aspect. And they sought feedback, and then based on that, they adjusted the parameters. And then they based it on a case by case basis on what aspects were passed and not. And then also, again, the main story here is it's important to establish a criteria beforehand to see, and then also to understand how it impacts like the patient. Uh, and implementing an ethical approach from the beginning of the test implementation to ensure that it aligns with human values the for the endoscopic pill. And then Lit 4, this one's a lot more comprehensive, involved the testing aspect, the design aspect, the industry quality standards as well. So this is to the right over here. This is like the actual robot, like the actual physical prototype. And then these are the professional requirements, business and design aspects. But these are like the regulatory requirements that's going to be of most concern. But the specific device that was implemented was a hybrid dot surgical robotic system. So what this could do is it could autonomously drill bones, or like not drill into bones uh, in specific locations where the screws are going to have to be placed by the doctor, but the drilling process is going to have to be done autonomously by the robot. But what they found out is the robot's able to accurately do it better and have less harm on a human being. So say uh, it's able to accurately determine the positions that are needed to drill into the bone and also minimize the harm or like the pain that the patient's going to feel. And then the information that backs this up is examples include position accuracy of less than 1 millimeter, orientation accuracy less than 2 degrees, and temperature change of less than 3 degrees Celsius. And then again, the way they found out how and where the positions should be is they analyzed different bone densities from different type of samples, from different type of representative samples. And then based on those bone densities, the amount of force, the amount of extraction, the speed of the drill, and then also electromechanical components of the actual hybrid dot controller drivers were used to see how it could be all encompassing of different type of bone densities. And this ties to kind of utilitarianism standpoint and making sure this incorporates for all different type of patients to minimize the most harm or to minimize harm to the most amount of patients. And then the result is this was successful and it received approval from the Hong Kong government. And similar to the endoscopic scope project, a lot of stakeholders were involved: mechanical, electrical, industrial, and all stakeholders. So again, this was approved because this was also approved by the Hong Kong government. And this is also the project also occurred in Hong Kong. And this is a Framingham study, but Framingham study was a study done in Boston, or not Boston, but Framingham, Massachusetts, where it analyzed the population there and they try to do studies on heart risks and risk of stroke. But this was done for like 5,000 sample population of 5,000 at the time for a sample population, and then but the main concern is most of the population there is of Caucasian descent, with about less than 4%. So the demographics at 1950 was 96 were of European descent, while 4% is of non-European descent. Uh, that rate's been kind of like that until about 2000s. Around 2000s, it was 81% Caucasian, while 19% were of other ethnicities. So there was a little more diversity in the sample population. But even then, around right now in 2025, the demographics have shifted to about 59% Caucasian population in the city of Framingham and about 41% of other ethnicities. So even when the population there's more demographic data and more diversity in demographic data, the challenge though is that the 50 years from about 1950 to 2000, that data has a heavy impact on how the actual algorithm is, because there's almost 50 years of data that are skewed towards the Caucasian like data set, and it mostly encompasses of that type of population group. So it didn't account for the type of heart risk that underrepresented communities would have. So what ended up happening is, uh, but the thing is that that study is still considered like a gold benchmark or the golden standard within the industry, and a lot of studies use that framework for their specific type of heart disease studies. Specific example is going to be project. It's called for risk of coronary heart disease, CHD. They used 42,540 data instances and 15 risk factors, all derived from the Framingham Heart Study. And the result that they got is there's a 96.25% validation accuracy. So in essence, this still is an accurate algorithm, but again, this doesn't account for the different type of populations and demographics, and that's one of the weaknesses in terms of this specific study. And next slide is going to be literature review summary. I think I kind of summarized it, but one was just baseline laws that the robot should follow to not harm the entities they're intended to serve. Second one is manufacturers and designers want to account for ethical changes and technical things in terms of legal compliance. They got to meet certain objectives, but also follow the legal compliance. L3 and L4, those basically were very similar in terms of they met their objectives, but L3 was in a shorter scope, and the scope was set before the project, and it changed based on the amount of risk that happened to the patient. So, when risk is defined, risk is the amount of chemicals or drugs that are deployed in the course of the endoscopic pill, which can be done autonomously. The Hyperjot surgical robot was successful in all aspects, from testing to quality to all aspects. Long story short, both were successful. Fragmented heart study just kind of serves more of an awareness about something that needs further research and study. Two specific questions that arise were, how will the data be achieved without violating the moral worth principle with Kant's deontological perspective? So based on Kant, he believed that if there's like a vested interest or a reason why someone's performing a good act, it might not have moral worth. So that's one aspect to kind of explore further on. Then situational application. So I think I mentioned earlier, given that Da Vinci robots are currently in level 0 and 1, the goal, at least this formulation, is going to be based on how to get it to level 2. And the first aspect is you want to incorporate the Asimov first law, so robot ethics, into the algorithm. So general idea, not harming a human being. Second one is not doing a moral act if a human being tells you to do so. And then third act is self-preservation. And then second one is going to incorporate both the Georgetown mantra, any type of engineering ethics such as ASME, IEEE. Those are also going to be incorporated into, those are hard-coded rules that are going to be implemented during the situational areas that the robot encounters. And then I just want to make it clear the way I'm kind of thinking of it is through how this would be for like a testing equipment, such for like environmental chamber or like a vibration shaker, where you could program it and then it could do it from start to finish. But then that machine can stop if there are any type of deficiencies, or not deficiencies, but if there's any type of problems. But given this is a surgical robot, it's going to have more capabilities such as 3D to see like organs and stuff that of that nature. So there's going to be more capabilities than like a test engineering equipment. And then from an engineering design standpoint, there needs to be safeguards in place with the surgeon during the duration of a surgery. It's kind of similar to a manufacturing robot, like a FANUC robot and like a worker. The worker's too close to a robot. The robot's going to stop in that situation, and then it's not going to engage. But one aspect I was also proposing is, based on industry 4.0 and 5.0, there should be communication protocols where they could get like text messages or emails, the doctors, to being able to see in real time what type of differences or discrepancies between the software and what their test code plan is. And then to step it up a notch, there's also next generation automated systems where the doctor would be able to actually click a button, and then it'll implement the action even when they're in another room, or say they're in ICU and not next to the robot or like the procedure. They could just press the button and the surgical robot can do the procedure. And then uh And then also the robot can detect if the robot has actually, or the surgeon has actually seen the message. If not, there should be ways to contact other or not engineers, but other surgeons that are credentialed to perform the surgical operation. There needs to be methods in place to make sure they're notified. If it's like a really strong emergency, an alarm system should be placed to make sure that it's transparent that there's a big issue and people should be informed. This ties towards benefits and truthfulness. And then the third concept is if like no one's answering, no one's coming to the rescue. At that point, the robot has to exercise ethical reasoning self-consciously and proceed in a manner to complete the surgery to the best of their abilities, and also based on, and there's a form of moral worth, or not moral worth, but they're somewhat responsible for the action that they do. That's kind of a hypothetical scenario for how to design the surgical robot to achieve level 2 and beyond capabilities. Over here, this is just a summary of some deontological mill and then virtue ethics concepts. So deontology, you could see the surgeon and engineering ethics from the way both parties are going to see it from each theory. So you can see that for surgeons and engineers, it's pretty similar in terms of both have Kantian concept of not harming patients long term. And for Georgetown, there's non-maleficence, justice, trust, and truth. Those are some of the concepts or pillars that are incorporated. And then for utilitarianism, a surgeon would approach it to make sure there's minimizing overall risk to the patient, and they have to use tools and surgeries, strategic methods to ensure that risk doesn't happen. And one aspect is benefits to make sure they're benefiting the patient, to act in the best interest of the patient. Utilitarianism standpoint for engineers is to design it in a way to maximize the probability of human death statistically, but it is to make very important to make clear that death is still possible. And virtual ethics just ties towards some of like the characteristics of the people. And as you can see, surgeons and engineering from both, the virtual ethics is going to be pretty similar. Uh, Concept of happiness is also going to be the same. Eudaimonia, in terms of both have a life purpose and they can find fulfillment through trying to satisfy another human being's needs. So sometimes for a surgeon, their view could be that through surgical robots, they could do a certain type of procedure that they can't physically do and serving a human's need. And then from an engineer standpoint, uh, just engineering solutions to being able to deliver surgical robots that have an impact on people. That could be a sense of happiness for them. And then for both, practical wisdom's quite evident. This is a relatively new field, so they're in dealing with different type of challenges, and both surgeons and engineering ethics, they have to implement from an ethical approach to make sure that this is being implemented and finding ethical ways to benefit humans and society. And the last slide is basically long term in terms of how this could impact jobs. So one of the examples they gave is anesthesiologist, that they, at least anesthesiologists, believe that they might be replaced. So one solution to this is that they could involve the bioethics committee with other like surgical robots committees, and then the designers, the engineers. There's also the people that code, software engineers. Make sure all parties understand each other's perspectives, and then being able to kind of cross communicate with each other and then find commonality and common ground, and then being able to discuss it. And then in situations where there are like actual risks towards replacement, there could be solutions to integrate people into the, make sure that people are still involved. So in robots, this could be used more as a way to enable or allow for human growth as opposed to creating job loss. So this could be used as a tool to enhance certain type of jobs. And one aspect is even looking at it from, because the reality is losing job, even after like someone does a job for 20, 25 years, the age of 50 and 60 is going to be hard for them to get a job in another field. So that ethical option all across the board is to make sure the robot serves more as a way to help the industry as a whole as opposed to dividing and outright replacing the job, because it does have a large impact, uh, both globally and also on a smaller scale for an industry. And that's where the ethical and robo ethics approach comes into play from an engineering and from a medical standpoint. And these are some references for this presentation. And thank you for spending the time to watch my presentation. I really hope this was very informative, and hopefully you enjoyed listening to some of the points I had to make. Thank you.